So factoring is enough of a topic in our course that we actually devote 2 different topic areas to it. We have an 8 and we have an 8 star this semester. So the topic 8 is sort of the basic level of factoring that everyone in Math 090 and 095 will do, and 8 star takes it a little bit further. So this is going to be intended to illustrate some of the more advanced topics that show up in 8 star, and I'll be talking in another couple hours with Math 090 about topic 8, and so both of those will go into our video channel for you to look at. But what I want to do is kind of tackle what is going to be one of the most intricate types of factoring problems that we'll do this semester, and that's this one, 9x to the 5th plus 24x to the 4th plus 12x to the 3rd. So let's first just talk about what the goal of a problem like this is to do. The goal of the factoring problem, 9x to the 5th plus 24x to the 4th plus 12x to the 3rd. The goal is for us to rewrite this expression as a product, as something times something, or possibly a product of 3 somethings if we need to. Right? The goal is to rewrite it as a product, multiplication, instead of as something that has additions in it. And the reason that we might want to do this is it's ultimately going to help us if we want to solve an equation involving a polynomial, because if I'm able somehow to factor this polynomial, and if the other side of my equation is equal to 0, then what that allows me to do, this is the holy grail of why we factor. What it allows me to do is it allows me to break apart this equation into 2 simpler pieces and then solve each of those simpler pieces separately. So the whole point of factoring is to give us a way to solve a polynomial equation by factoring and then splitting apart each of the factors and giving it its own equal to 0, and each of those factors is much simpler, and then we'll be able to solve that simpler equation. So we're not going to go all the way there on this problem. Instead, I want to illustrate just a strategy for how to solve, or how to actually do the factoring step on something like this. So the first step in a grand strategy for factoring is to first of all think, is there a greatest common factor to all of these 3 terms that we can bring out of all 3 of them? And so here that answer is going to be yes. So I also want to use this opportunity to introduce a device that, depending on who you talk to, is sometimes called a multiplication lattice or multiplication grid. Probably most of us haven't done it this way when we first learned to multiply in elementary and middle school and high school, but the new math and the Common Core is using a lot of techniques like this. So I think this is as good a time as any, and I actually have kind of taken a liking to it since coming to it. So here's how I like to think about it. We have 3 terms, 9x to the 5th, 24x to the 4th, 12x to the 3rd. And the idea is, if all 3 of those terms have something in common, like for example, the number 3, 3 goes evenly into 9, it goes evenly into 24, it goes evenly into 12, then that means that I can factor out a 3 from each of these terms, and what I'll have left over is 3 times 3 gives me 9, 3 times 8 is going to give me 24, 3 times 4 is going to give me 12, and I'll still have x to the 5th here, x to the 4th here, x to the 3rd here. Right? And this little factoring grid that I've just put together is kind of a nifty little bookkeeping way to keep track of what looks like in algebra the following factorization. It looks like bringing out a 3 outside of our parentheses and leaving on the inside of the parentheses the cofactor 3x to the 5th plus 8x to the 4th plus 12x to the 3rd. And so the moral of this story is that what we're essentially doing is we're reversing the process of distributing multiplication over addition. Right? If I were to try to simplify this expression to get rid of the parentheses, I would remultiply this 3 back into all 3 of these terms, and we would end up back where we started. Right? So that's the whole point of factoring, is to reverse the distributive property of multiplication over addition, which is no mean feat. Right? There's a lot of different aspects to that strategy, and we're going to talk a little bit more about some of them. But I often like to use these grids. So if you look back in all my previous videos that I've done for talking through factoring and multiplying for this course, you're going to see a lot of this kind of grid stuff. So if you like it, use it. If you find a different way to connect with this technique, then use that instead. But give this a shot, because I personally find it to be really powerful. So we've seen now that we can factor a 3 out of everything, but we can actually do better than that. Because these 3 terms not only share a 3 in common, but they also share a bunch of powers of x in common. Right? for example, I could bring an x out of all three of these terms. All three of these terms have an x in them. And after all, since we just learned that multiplying powers of x leads to adding their exponents, we can convince ourselves that if I bring a single power of x out, then the cofactor inside is going to have one less power of x and be 3x to the fourth plus 8x to the third plus 12x squared. Right? Because if I were to multiply, for example, 3x times 3x to the fourth, the total number of powers of x I'm going to have is going to be 1 plus 4, and that gives me my 5. But we can keep going, because there's more than just one power of x in common to all these terms. There's, in fact, as many as 3 powers of x that we can bring out of all 3 of these terms. And if I bring out all 3 of those powers of x, that leaves me with 3x to the 2, 8x, and then a 4 without any x's as my cofactor. So now my factorization looks like, whoops, looks like I had a 12 there where I meant to have a 4. Sorry if that was confusing. There we go. So now I've brought out as much as I can bring out, because now 3x squared, 8, and 4 don't have anything that's common to those 3. Right? There's no number besides 1 that goes into 3, 8, and 4. And there's no number of powers of x that exists in all 3 of these terms, because in particular this last term doesn't have any x's at all. So 3x to the third is called the greatest common factor of these 3 terms. And now I've succeeded in the first step in my grand strategy for factoring, which is to factor out the greatest common factor. But the story doesn't end there, unfortunately, because we still have this expression, 3x squared plus 8x plus 4, that we might still be able to factor. We might still be able to break that apart into another multiplication. So that's where now we start to try some of the other methods that we learn. One of them is called the sum and product method for factoring a trinomial. So this now has 3 terms in it, so we call it a trinomial. So the sum and product method is one approach to that. And the AC method is another, and that's the one that we are going to talk about right now, how to use on this particular trinomial. And the reason that the AC method is useful for this particular trinomial is that in front of the x squared, this number, this coefficient right here, is not 1. So anytime we have a trinomial whose leading coefficient is not equal to 1, this AC method that we're about to talk about is going to be our best option for moving forward in factoring. So here's how the AC method works. I'm going to set up another factoring grid for inspiration. Again, what we're going to try to do is factor 3x squared plus 8x plus 4. And the issue here is I want to find a pair of factors. Like maybe I'm going to get my 3x squared from a 3x times an x. And maybe I'm going to try to get my 4 from a 2 and a 2 or something. Or maybe a 4 and a 1. Let's suppose this is what we try. Then if I try this, if I multiply, in other words, what I would be doing is I would be trying to factor this as 3x plus 1 times x plus 4. If I tried it this way, then I could check my work by multiplying everything else back out. 3x times 4 is going to give me 12x. And then x times 1 is going to give me 1x. But then if I multiplied this all out and I combined these 4 terms together, I would get 3x squared, I would get 4, but I wouldn't get 8x. I would get 12 plus 1, or 13x. So if I multiplied this back out, I would get kind of too much. 3x squared plus 13x plus 4. So this isn't quite the right factorization, but it seems like it's pretty close, right? Because it gives me the first term correctly and it gives me the last term correctly. So it's really just this middle term that causes us some difficulty. So the question really is, how do we split up this middle term in a way that's going to make factorization possible? So this is where the AC method comes in. And the way the AC method works is we identify the 3 coefficients of this polynomial, which we usually call A, B, and C. respectively. A is the coefficient of the x squared, b is the coefficient of the first power of x, and c is the constant. And we multiply together the a times the c. So 3 times 4, 12. And then what we do with that number is we play a little game that I like to call the sum and product game, wherein what we want to do is find a pair of numbers that multiply together to give me that 12. So I need the product of these two numbers to be 12. But at the same time, I also want the sum of those two numbers to be equal to my b, which is 8. So AC ends up as the product, and B ends up being the sum. So the question I have for you is, what pair of numbers multiplies together to give me 12, but also adds together to give me 8? 6 and 2 will do it. So we have a winner for our sum and product game. And what we do with that 6 and 2 is we then make the decision to split up our middle term, our 8x, into one of my boxes with 6x in it, and the other box will have 2x in it. So 6x in one box, 2x in the other box. It turns out that it doesn't matter which box we put which in, so I'm just going to put those where I just did. So this little sum and product game is something you'll get plenty of opportunity to do, because it also works for factoring simpler polynomials as well. So now we have all 4 of the boxes inside of our grid filled out. Now we have to fill out the outside somehow. And the way we'll do that, the way to get the process started, this is a step everybody forgets, is we're first going to look for a greatest common factor between these two terms, 3x squared and 6x. What do both of these terms have in common that I can bring out into the front? What do 3 and 6 have in common? 3. What do x squared and x have in common? They have an x. So I'll bring out 3x as the greatest common factor. What's great about that is that now that I did that step, the rest of this table is going to fill itself in. Because I just have to answer, what's the missing factor between 3x and 3x squared? It's x. 3x times x gives me 3x squared. What's the missing factor between 3x and 6x? 2. 3x times 2 is going to give me 6x. And then it's what's the missing factor between x and 2x? That's 2. And we can check that 2 times 2 gives me 4 in the last box, which means we did it. We've found out how to factor that polynomial in the blue. It factors as 3x plus 2 times x plus 2. Sorry, let me get some space on that. 3x plus 2 times x plus 2. And then let's not forget our 3x to the third out in the front. So that was a pretty involved factoring problem, because it gave us a chance to really use 2 different factoring methods. The greatest common factor method, which should always be the first thing you think about in a tricky factoring problem. Always look to see first whether there's a greatest common factor you can bring out, which in this example there was, 3x to the third. But then once that greatest common factor is brought out, there might still be more work to do. And that's where you plug in some of the more challenging techniques that we learned this semester, the most challenging of which is the AC method that we just talked about, where the first thing we did is multiply the A and the C coefficients, 3 times 4 to give me 12, and then look for a pair of numbers which multiply together to give me 12, but also add together to give me 8. And the answer to that was 6 and 2. We used that 6 and 2 to split up our middle term into these 2 boxes, and then use the greatest common factor of that first row, or really you could choose the first column, or you could choose the second row, the second column, it doesn't matter. Just pick a row or pick a column, bring out the greatest common factor of that row or column. And then that gets the ball rolling to fill in the rest of the factors, and that gives us our factorization.